The next talk we'll be having Dr. Lekshmi Ramesh, who will be talking on multiple support recovery from very few measurements per sample. Lekshmi Ramesh recently completed her PhD from the Department of IEEE-IISc, where she worked with Professor Chandramurthy and Professor Himanshu Tyagi. Her interests are in the area of compressed sensing, statistics, information theory, and privacy. Welcome, Rashmi, and the floor is all yours.
Yeah, hi everyone, and thank you for giving me this opportunity to present my work, and thank you all for joining. I'll just share my screen in a second. Okay. So I hope my screen is visible.
Yes, it is.
Yeah, thanks. Okay, so I'll be talking about multiple support recovery using very few measurements per sample. This was sort of like the one part of my thesis that I'll be presenting, and this is joint work with my advisors, Professor Chandra and Professor Himanshu. So this is the outline of the talk. I'll start by explaining the problem setup, as in what the problem of multiple support recovery is, and then I'll also mention some background related work. And then I'll move on to point an interesting regime of parameters in which this problem is not very well understood and like no theoretical guarantees were known. And then I'll move on and describe a spectral algorithm that we use to solve the problem of multiple support recovery in this regime of very few measurements. And following that, I'll describe an upper bound on the sample complexity of this problem that we get by analyzing this problem. And I'll finally conclude and explain some further directions that people can look at. Okay, so I'll start by explaining the problem. So it's a simple problem to explain. So this problem basically consists of a bunch of n samples. So these are x1 through xn, and each of these samples is in d dimensions. And each xi has exactly k non-zero entries. Okay, and the locations of these non-zero entries, so the indices at which these non-zero entries occur for each xi, we'll call that the support of the sample. Okay. And the assumption here is that the supports of these xi's are drawn from a small set of allowed supports. Okay, so n here could be a large number. We could have a huge number of samples, but their supports are like relatively like few or small. So each xi's support is drawn from this small set of L allowed supports. Okay, so each Si here, it denotes a subset of the indices 1 through D, and it's of cardinality exactly k. Right, so just to pictorially represent this, let's say we look at the simple case where we have two allowed supports. So the parameter L is 2 here. And let's say the two supports are basically the indices 1 and 2, and the other one consists of the indices 3 and 5. So if these are the two allowed supports, then the samples would basically look like this. So each xi would have non-zeros either at the locations 1 and 2 corresponding to support 1, or at the locations 3 and 5 corresponding to support 2. Right? So this is how the samples look like. We'll move on and describe a model for these sort of samples, a probabilistic model and so on later on in the talk. But right now you can just think of there being like sufficiently many samples or like a constant fraction of samples drawn from each support. Right. But we don't have direct access to these samples. What we observe are low dimensional projections of these samples. So each xi gets multiplied by a matrix phi. So this phi is called a measurement matrix. And these measurements that we denote by yi, these are what is available to us. Okay. So this phi, each phi is basically an m cross d matrix with m being much less than d. So what we observe eventually these yi's, they have a much smaller dimension, so to speak. They are just m dimensional vectors, which is where m is much smaller than the dimension d of the samples. Right, and the goal here is to basically recover this underlying set of L supports given the knowledge of the phi's and the yi's. Okay, so that's the problem. And why would we want to study such a problem? So here's one application that I'll quickly describe, which is that of using this formulation to study coordinate clustering or feature clustering problem. And just to fix some ideas, let's say the problem here is basically that there is this is the problem of distributed user profiling, where we have a bunch of n users and each user has a huge d-dimensional profile vector, and the entries of vector could represent, ratings or preferences for certain features. So you could think of retaining like high preferences or very low preferences. So this is like a sparse vector that each of these users has. And these users want to communicate their profile vectors to a center. And so what they do for that is they compute low dimensional sketches. So these are the phi xi, the measurements. And these low dimensional sketches are sent to a center. And the center, what it wants to do is to figure out features or coordinates that decide user groups. Okay, so so let's say in this given population there will be user groups determined by so users within a group would have preferences for the same features, and the center wants to recover features that decide these user groups. So it's exactly the same as the problem that we saw earlier. Right, so that's just one example application, but let's look at some more background on what is known in this problem and what has been studied. So this is related to a line of works in this area of mixed linear models, where the idea is to study this heterogeneous population and you want to fit a linear model to each group. So there are subgroups in a population and you want to fit a linear model within each group. And it's also related to this problem of mixture of linear regressions and phase retrieval, which I'm not sure if you are familiar with. So these are like well-known problems in signal processing. So phase retrieval is a special case of this multiple support recovery problem that we just saw. And there is also some very recent work on a slightly more general setting of learning mixtures of low-rank models. Right, and the focus usually has been on a worst case formulation of the inputs, and the goal is usually to recover the data vectors themselves and not the support or some other properties of the data vectors. Also, current algorithms, they usually require at least taking k measurements. So for the case when we are looking at sparse sample, current algorithms require taking at least roughly k measurements per sample. And the question that we would like to answer is whether this requirement, it can be reduced. And that's because when we have a huge number of samples, we would expect that we can reduce the number of measurements that we need to take per sample, right, at the cost of maybe taking more samples. And we should also expect this because there is some joint structure across samples, because the supports would repeat, right? The number of samples is huge and the number of allowed supports is small. Obviously, there will be lots of samples have a common support. So there is some joint structure and we should be able to exploit that and eventually cut down on the number of measurements that we need to take per sample. Right, so this is roughly the question that we'll try to answer. And this question is sort of well understood for the special case when there is a single support, right? So let's say we look at a special case of the problem where this parameter L is equal to 1. So there is just one, so the set of allowed supports, it's basically just one support. Okay, so all the samples have just some common shared support. And for this case, it's understood. So the number of samples that we need, that needs to, so we'll denote that by n star. And we'll look at how it needs to scale in terms of this ratio k over m. So recall that k here is the size of the support. So in this cartoon, it's just 2. And m is the number of linear measurements that we are taking per sample. Okay. So you'll note that we have just demarcated this x-axis into 2 regions. So when we are on the left hand side, so this is the measurement rich regime, when you have at least roughly k measurements per sample. So this ratio is smaller than 1. In that case, it's known that the number of samples, it needs to scale as k over m log d. On the other hand, when you move to the right side of this plot, which is when you have very few measurements per sample, so fewer than k measurements per sample, in which case this ratio would be greater than 1. So in this measurement constraint regime, the behavior of n star, or the number of samples that you need, that completely changes, and it now needs to scale like k squared over m squared log d. So it becomes quadratic in this ratio k over m. Right. So the special case, from what we understand, we know that it is possible to operate in the regime of very few measurements per sample, but at the cost of requiring more samples. So you need more samples when you're in this regime. And this follows from some of the previous works in this literature and one of our recent works. Right. So that gives us some understanding for the special case when there is a single or a common support throughout. And so what happens in the case when we have multiple supports, right? So in that case, there's basically two sets of unknowns. The first set of unknowns is the labels that associate each measurement to the support. So that the set of those labels would basically tell you for each measurement which support it was generated from. And the other set of unknowns is basically the set of L supports. And so if you had knowledge of the labels, then what you could do is you could group together measurements that are coming from the same support, and then the problem would reduce to the previous problem that we saw, the special case of a common support. So if you had the labels, you could group together measurements coming from the same support, and within each group you could use a common support estimator or algorithm. So then it's easy, so you can do that. On the other hand, if you have sufficiently many measurements per sample, so roughly of the order of k measurements per sample, then you can use standard compressed sensing algorithms, run them measurement by measurement, and recover each support individually. Okay, so for both these cases, we know how to solve the problem. But it's not clear how you would solve this problem if you did not have the label information and you were constrained to operate in the very few measurements regime. Okay. Right, so these are two concrete questions that we would like to answer. The first one is whether it's possible to do support recovery when the labeling information is absent and you observe fewer than k measurements per sample. And we'll see that this is possible, and we'll see an efficient algorithm that can do multiple support recovery from very few measurements. And the other question that we would like to answer is the quantitative question of, if you can recover, then how many samples do you need to perform this recovery? And again, we'll see by analyzing this algorithm that roughly KL over M to the 4 samples suffice for multiple support recovery. Okay. So let's see what the algorithm looks like and how we'll solve this problem. And so it's useful to try and build some intuition and see how we would solve it for the case of fully observed data. Okay. And just for the rest of this talk, I'll assume that these L supports, they're disjoint, and that we have a constant fraction of samples coming from each support. Okay, so I still haven't described to you the generative model that we use, but the details of that can be found in the paper. Okay. So what would we do if we had full access to the samples, right? We could just look at the samples and determine what the support is just by reading it off. But what is a method to do this? And the answer comes, the answer for this, I mean, you can get it if you look at the structure of the sample covariance matrix. Okay, so this is the idea in picture. So let's say capital X here, that's your data matrix. So each column represents one sample. Okay, and so there are two kinds of supports here. You can see that. So the first sample and the third sample have a common support. So that's the first support consisting of indices 1 and 3. And there is another support. So samples 2 and 4 have a second kind of support. Okay. And if you take this data matrix and you construct the sample covariance matrix, you can check that if you permute the rows and columns appropriately, then it would lead to a block structure, right? So if you permute the rows and columns in such a way that indices corresponding to the first support appear first, followed by indices corresponding to the second support, then these non-zero entries would just align on the blocks. So you get this block structure. But how do you figure out this permutation, these permutation matrices, which is basically equivalent to figuring out the supports, right? So how do you do this in a principled way? And you can see that the answer to that is given by simple observation from linear algebra. This permutation, or basically the underlying supports, they can be found using eigenvectors of the sample covariance matrix after some normalization. So what you essentially need to do is just compute the sample covariance matrix, take the second leading eigenvector of the sample covariance matrix and look at the signs of the entries. And for the case, so this works for the case of two unknown supports. So there are two unknown supports here. So if you look at the sign, then all the coordinates with a plus sign, right? So that have positive entries in the eigenvector, they would tell you what the first support is or one of the supports is, and all the entries with a negative sign would tell you which indices constitute the second support. So that's like a simple algorithm for the case of two unknown supports. On the other hand, if you have more than two supports, which would essentially mean that when you get the right permutation, there would be like L blocks on the diagonal. In that case, you need to use more eigenvectors. So the top L eigenvectors need to be used, followed by a nearest neighbor sort of step. And this is a well-known algorithm. It's used in spectral clustering, community detection, and several other algorithms. Right, so that's the idea. So we now understand how to do this in a principled way if we had full access to the samples. But the question is, how do we do this if we just have very few linear measurements from each sample, right? So can a similar approach still be used? And the answer is yes, we'll still use this spectral clustering based approach, which basically means that we'll use eigenvectors followed by a k-means kind of step. But instead of using it on the xis or the data, the original data, which we don't have now, we'll use it on some kind of a proxy estimate for the data. So what we'll do is we'll first compute certain second moment estimates. We'll call these, or we'll denote these as AIs. So what these AIs are is basically you look at each measurement yi, you'll pre-multiply it with the transpose of the measurement matrix, and you'll treat this as some kind of proxy for the true sample. And then what you do is you'll take entry-wise squares. And this is just to make it robust to cancellations, because we'll be doing a lot of averaging and other things. These entry-wise squares ensure that some robustness to cancellation and things like that. And this is what we'll call some sort of a robust like second moment estimate for the data. We'll denote these as AI. And then we'll use the sample covariance matrix of the AI to figure out the blocks or the supports. And this works because the sample covariance matrix of the AIs has a nice structure. So for any two coordinates u and v that lie in the same support, this pairwise product of the entry u and v of AI, so AIU times AIV, it would be a large number. And you can formally show this. And for any two coordinates u and v that belong to different supports, this pairwise product would be small. Right, so essentially what this is saying is that the sample covariance matrix of the AI, which consists of these kind of pairwise products, it will retain this sort of a noisy block structure. So it would have large values on the blocks and small values in the off block entries. And that is the important property that you need for spectral clustering to work. Right, so this kind of a block structure is still preserved even after you did all this. So we didn't have access to the samples, but we constructed some proxy version of the samples, computed the sample covariance matrix using those proxy samples, and it still works out because we can show this formally that the block structure exists. Okay, and so once we can show that such a block structure exists, then it's straightforward. We just apply spectral clustering on the sample covariance matrix of the AIs to recover each of the underlying supports. But one issue here could be that this sample covariance matrix is a huge D cross D matrix, and it could be computationally intensive to run something like spectral clustering on it. So what we do to make this less intensive is that we'll first estimate the union of the L supports, and then we'll run spectral clustering restricted to this union. And this is useful because the size of the union can be much smaller than the size of the original samples, which is D. Okay. Right, so this is the full algorithm. So we'll start by computing these second moment estimates using proxy samples. What we'll do, so now we need to do two things. The first thing is to estimate the union of the supports, and the second thing is to partition that union into L different supports, right? So how do we estimate the union? To estimate the union, we'll use the sample mean of the AIs, and we'll pick the top KL coordinates of this sample mean as our estimate for the union. And once we have the estimate for the union, we'll restrict each of the AIs to just coordinates in the union, and then compute the sample covariance matrix. We'll call that T, and then run spectral clustering. So by spectral clustering, I basically mean computing the L leading eigenvectors and doing a nearest neighbor step, right, to partition the union. Right, and you'll note that what we are essentially doing in steps 2 and 3 is that we are working with second order statistic of the data to recover the union. So this is the second order statistic of the xi, and using some sort of a fourth order statistic of the data to further partition the union. Okay, so I hope the algorithm is clear. And so let's now quickly see how we could analyze this algorithm, which would tell us or which would give us an idea of how many samples we need or how many samples would be sufficient to do multiple support recovery. Right, so we'll analyze this algorithm under some assumptions on the data and on the measurement matrices, and you can find the details of this in our paper, which I'll refer to at the end. So we'll work under a sub-Gaussian generative model assumption on both the samples and on the measurement matrices. And what is our goal here? So what is our recovery criterion? The recovery criterion is to approximately recover all the supports up to a permutation of the support labels. Okay, so it's not important which support we call support 1 or support 2. We just want to recover all the supports approximately up to this sort of a permutation of the support labels. Right. And what is the quantity that we're trying to characterize? This quantity is the sample complexity, which is the smallest n for which we can find an estimator that satisfies our recovery criterion. Right. We'll call that as n star. And what we'll see in the next few slides is the following result. So remember that we were operating in this measurement constrained regime. So when we are operating in this regime of very few measurements per sample, where m is less than k, in that case, n star scales roughly as kl over m to the 4. Okay, so this is, there are some hidden parameters here. There is some log dependence on the dimension d of the samples. So I'm not showing those dependencies here, but this is the dominating term. So sample complexity scales as, or an upper bound on it, looks like kl over m to the 4. Okay, so how do we show such a result? And so here's a quick proof for this theorem. So we'll analyze each of the two steps in the algorithm separately. So we'll first analyze the union recovery step, which is to show that looking at the sample mean of the AIs gives us a good estimate for the union. Okay. And we can show that that estimator works once we have roughly kl over m squared samples. And this follows from one of our previous works, which shows that the union recovery step is good. And once you can show that the union recovery works fine, you need to show that the second step where you partition it, that works fine. And for that, you first start by studying what the expected behavior of this clustering matrix looks like. So recall that we construct this clustering matrix, which is the sample covariance matrix, and then we run spectral clustering on it. We first show that the expected value of this clustering matrix that has the desired block structure under the right permutation, right? It has the desired block structure in the sense that if you permute the rows and columns appropriately, it would have large values on the blocks and some small noise on the off block entries. And so once you can show such a properties, it would such a property, it would basically say that it's good to run spectral clustering on this matrix, right? Uh, and why is it good? So let's quickly take a look at that. It would be good. It's good because if the expected clustering matrix has a block structure, then its eigenvectors also have some nice structure in the sense that if so let's say this is what the expected T matrix looks like. It has 3 blocks, so which let's say there were 3 unknown supports. And then if you look at the L leading eigenvectors of the expected T matrix, then those have a nice structure too, in the sense that one can formally show that their rows basically there is a repeated row structure in this matrix of eigenvectors. Okay, so all coordinates which belong to the same support would basically have exactly the same row value in this matrix of eigenvectors, which means that you could think of these rows as points in some L dimensional space, and you could run a nearest neighbor step on these scale coordinates or these scale rows, and that nearest neighbor step would basically group rows together. So similar rows would get grouped together, and you would be able to recover the supports. Right. So basically, it's a nearest neighbor step would partition the union of size k times L into L disjoint subsets. Right. So, but we don't have access to the expected clustering matrix. We only, of course, have access to a sample version of it, which we construct using our proxy samples. And we can show that the sample version of the clustering matrix tree suffices. So it's just as good once you have roughly KL over M to the 4 samples. Right. So, and how do we show that? The first thing is to show that the eigenvectors of this sample version T and the expected T matrix are close once this quantity is small. So what is this quantity? It's the largest eigenvalue of this sort of error matrix. So the error between T and its expected value. So if you can show that this largest eigenvalue of this error matrix is small, then it would imply that the eigenvectors are close. And so the key step here is to show that this quantity is small. And so for that, we need to look at the structure of this clustering matrix. It's a sum of rank 1 matrices that have heavy tailed entries and dependent entries. So because of which you can't use some standard methods that are there in the literature. And we basically built on a result from a paper by Rudelson, using which we could bound this quantity under a much more relaxed assumption on the moments, okay, of the AIs basically. So standard tricks don't work here because the entries of T, they are basically dependent random variables and they're also heavy tailed. Okay, so this result basically lets us bound this quantity, which gives us the theorem that we saw earlier. Okay, so that's basically the analysis of the algorithm that gives us that sort of a performance guarantee. Okay, so with that, I'll conclude. So what we saw was a spectral algorithm that can do multiple support recovery from very few linear measurements. So we could operate in this regime of fewer than k measurements per sample and still recover the L underlying supports. And we saw that it roughly requires KL over M to the 4 samples, and this is much more compared to what we need for the case of a single support. And there's several directions on which one can work on. So first one maybe is to get rid of the assumption that the supports have to be disjoint. So the case of overlapping supports would be a very interesting direction to work on. and the other one is basically lower bounds for this problem. So what we saw today was an upper bound on the sample complexity. So it would also be interesting to work on lower bounds. Right, and if you're interested, you can look at this paper that's available on arXiv. And so thank you for listening, and if there are any questions, I can take those.
Yes, thank you, Lakshmi, for the interesting talk on sparse recovery. It's currently one of the hot topics among many research domains, and I'm sure you'd have intrigued people from working in similar or even different research areas. So we can now take some questions from the audience. So if anybody from the audience has any questions, you can ask now. So it seems there aren't any questions. So Lakshmi, can you stop sharing the screen?
Yeah, sure. Yeah.
So thank you once again, Lakshmi, for delivering this talk. So on behalf of IEEE-IISc ComSoc and SPS chapters, please accept this memento, and we wish you all the best for your future endeavors.
Yeah, thank you. Thanks a lot.